Friends, here we would like to find the expression of mass moment of inertia of a rod having uniform thickness. So this is a rod, friends, and it is having uniform thickness. So that thickness is not important over here, so I have not shown in this particular picture. So what is important is the length of the rod. Okay, so let's say L is the length of the rod, and we would like to find the moment of inertia of this particular rod. And let me call the total mass of the rod is m. Okay, so this rod has got overall mass as m. So this rod has got total mass as m and its length is L. Now we would like to find the moment of inertia of this particular rod about some axis. So there are two possibilities of axis. The first axis may pass like this through its center. Okay, so here there will be center of this particular rod and the axis may pass like this. So this is the axis about which it may rotate. Okay, this is one possibility, friends. The another possibility is that you may have an axis at its end. That is also possible case. So we can say that so an axis may pass from the one of end of the rod like this. This is another case. So this rod may be rotating about this particular axis. This rod may be rotating about this axis. So let me call this point as point O, this point, the center point as point C. So when the rod rotates about this axis, its moment of inertia will be IO, and if the rod rotates about this axis, its moment of inertia will be IC. Okay, so we have to find the expression for IC and IO. So first I'll take case 1. I would like to find the moment of inertia of this particular rod about an axis passing through its center. So I'm going to take case 1, that is moment of inertia of rod about an axis passing through its center and perpendicular to its length. So for that I'll be considering a small portion of the rod. Let's say this is a small portion of rod. This small portion has mass dm. Thickness of this mass is going to be dx. So I have considered a small portion of rod which is having thickness dx, right? And its mass is very small mass dm. And the distance of this particular small mass from this axis of rotation is I am going to take as x. So let me again repeat it. I have considered a very small mass dm at distance x from the axis of rotation which is passing through the center of mass, and the thickness of the mass is dx. So in this particular case, so here I can write down the mass per unit length. Simply it is total mass, that is capital M, divided by total length, capital L. That will be also same as, if I take this particular small mass, so that will be same as dm divided by its length, that is dx. This is going to be same, right? So from this particular expression, so I can get the expression of small mass, that is dm, which will be equal to m by L into dx. Okay, so I have got the amount of mass, that is dm, which is at distance x from the axis of rotation. Therefore, moment of inertia of dm, I am just taking dm, friends, not total rod, about axis of rotation. This axis of rotation, friends, which is passing through C. This is very simple, we have already defined it. So mass into square of distance, that is x square into the mass. So this is nothing but the moment of inertia of this particular mass. Now I would like to find the moment of inertia of total rod. So I will have to start from this point and I have to continue up to here. Okay, so if you are at this particular point, value of x is going to be minus L by 2 because you are at the left hand side. Okay, and when you are at this particular point, your x is going to be plus L by 2, right? So you are going to move this mass starting from left, that is here. So you will assume your mass is here. So when your mass is here, x equal to minus L by 2, and gradually you will keep on shifting your mass towards right so that you can complete the entire rod. So this procedure is called as integration. Therefore I can write down, so moment of inertia of rod. So now small dm, instead of small dm I am writing full rod. So moment of inertia of rod about axis passing through center of mass or passing through point C. Here I am going to integrate this quantity like this. So x square dm will be integrated. So your starting point will be x equal to minus L by 2, which is this leftmost corner here, and the right hand corner is going to be x equal to plus L by 2. So I'll write x equal to plus L by 2. So we are integrating from minus L by 2 to plus L by 2. So we have got the limits over here, friend. Now the value of dm we have to substitute. So the value of dm we have got as m by l into dx minus l by 2 lower limit to plus l by 2 upper limit, then x square as it is, and the value of dm is m by l dx. Now why we have put this value? Because I cannot integrate, because this variable is x and this variable is m. So to integrate we should have same variable throughout. Okay, so now this m by l will come outside. So this I am writing moment of inertia of a rod about axis passing through point C. So this is this axis. So I am going to write this as IC, this is friend IC, and that is equal, m by l is constant, mass of the rod divided by length of the rod, and the inside will be getting minus l by 2 to plus l by 2 x square dx. Now the integration of x square is going to be x cube by 3 m by l x cube over 3. The limits are minus l over 2 to plus l over 2, that is l by 2 over here. So if you simplify this, I am going to put upper limit. So this 3 also will come outside because constants, m by 3l. The inside will be having l by 2 cube. So l by 2 cube is going to be l cube by 8, and then we will have minus of minus l cube by 8, like this, friends. If you simplify this further, you will be getting moment of inertia IC as m over 3l. This is going to be plus, so you will be getting l cube by 8 plus l cube by 8, so it will be l cube by 3, so it will be l cube by 4. And when you simplify this, you will be getting moment of inertia of a rod about an axis passing through its center and perpendicular to its length will be, this L and L will be getting cancelled out, so ml square by 12, ml square divided by 12. So this is the expression of moment of inertia of a rod about an axis passing through its center and perpendicular to its length. Okay, so the next case will be the moment of inertia of this rod about this axis which is passing through one of its end. Okay, so that is going to be case 2. So case 2 is very simple. So now if you want to get the case 2, friends, it is the moment of inertia of a rod, of this particular rod about this axis. Okay, so I can use the parallel axis theorem. So by parallel axis theorem, friends, I can say IO equals the moment of inertia of the rod about its center, about this axis passing through center, so it is IC plus mass of the rod, that is m, into square of distance between them. So square of distance between them is going to be L by 2. This distance is, friends, L by 2, as it is clear from the diagram itself. So square of this distance, so L by 2 square, right? So if you simplify this, friends, you will be getting IO, the moment of inertia of the rod about an axis which is touching the one of the end of the rod. So it is going to be IC is nothing but ml square by 12, and this is going to be ml square by 4. So ml square by 12 plus ml square by 4. So it is 1 by 3. So like this you can find out the moment of inertia about this axis.